When you apply a lateral force, or shear stress, to a rigid solid, it resists. It holds its shape until it finally cracks. But apply that exact same force to water, and it simply yields. That yielding is the strict physical definition of a fluid. A fluid is any substance, a liquid or a gas, that offers virtually zero resistance to shear stress. Because it has no fixed shape, the standard physics toolkit we use for rigid blocks and levers suddenly falls apart. We cannot track the center of mass of a substance that constantly deforms. Since the substance deforms and fills any container, we stop tracking it as a single object. Instead, we map the properties of the space it occupies, the pressure at every point, and the energy it carries as it flows. We will build this mental model step by step, starting with the mechanics of fluids at rest, then observing the laws of motion, and finally introducing the friction of the real world. Mastering these rules allows us to predict everything from the blood pumping through your veins to the aerodynamics of a jet in flight. Let's start with the simplest state, a confined fluid, completely at rest. In this environment, all forces are perfectly balanced. We can't easily measure force acting on a single fluid particle, so we measure pressure instead. Pressure is the normal force acting uniformly over a specific unit of area. In the 1600s, Blaise Pascal realized that if you apply pressure to any point of a fluid enclosed in a container, that pressure is transmitted equally and undiminished in every direction. This diagram shows how we exploit Pascal's law to generate a mechanical advantage. If we push down on a small surface area, A1, with a specific force, F1, we create a uniform pressure field inside the fluid. Because that exact same pressure must reach the other side, providing it with a much larger exit area, A2, means the force spreads out over more space. The result is a multiplied exit force, F2. This is the principle behind the hypodermic syringe. A thumb pushing down on the large plunger translates into an immense, localized pressure at the microscopic area of the needle tip, easily piercing tissue. But we must also consider what happens when we remove the lid and expose a fluid to gravity. In an open container, the pressure at any given point relies strictly on the depth of the fluid, its density, and gravity. This is gauge pressure. Notice that the shape of the container is completely irrelevant to the calculation. This applies to the atmosphere itself. Atmospheric pressure is the literal, physical weight of the air column pressing down on us. In this mercury barometer, the fluid rises and falls in response to the weight of the sky. In the realm of statics, a fluid acts as a transmission medium, allowing us to manipulate force by altering geometry and depth. Now, if we allow the confined fluid to freely flow, the static forces we have just observed immediately translate into dynamic motion. In a steady, ideal flow, fluid particles follow precise paths called streamlines. As long as the flow remains steady, these streamlines never intersect. This diagram illustrates a spatial problem. What happens to a specific volume of fluid when the pipe suddenly narrows? Because liquids are incompressible, the fluid cannot just pile up. To squeeze into the bottleneck, the exact same amount of mass that enters the wide section must pass through the narrow section in the same amount of time. This gives us the continuity equation. Area times velocity equals a constant. If the cross-sectional area decreases, the velocity must proportionally increase to compensate. The continuity equation ensures that mass is never lost or gained in the stream. It is the physical manifestation of conservation of mass. There is an energetic cost to these sudden changes in velocity. In the 18th century, Daniel Bernoulli figured out exactly what that cost was. Bernoulli's principle states that for a steadily flowing ideal fluid, the total mechanical energy per unit volume must remain constant. This is a balance of static pressure, kinetic energy, and elevation energy. Since the total energy cannot change, the fluid makes a physical trade-off. If its velocity increases horizontally, meaning its kinetic energy rises, its internal static pressure must drop to keep the total energy balanced. This trade-off drives the phenomenon of dynamic lift. Look at the curve or camber on the top of this airplane wing. As the plane moves, the shape of the wing forces the airflow over the top to travel faster than the air moving underneath. Faster air results in lower pressure above the wing, creating a net upward force. This same pressure differential dictates the Magnus effect in sports. When a bowler spins a cricket ball, the seam drags air unevenly around its surface. The air moves faster on one side, dropping the pressure there and pulling the ball into a curve during flight. This energy conservation also controls how water drains from an open tank, a relationship known as Torricelli's law. If you punch a hole in a water tower, the speed of the escaping water is perfectly equal to the square root of 2 times gravity times height. That is the same speed a solid block would reach if dropped from that exact same height. Bernoulli's principle describes a constant energy balance. Fluids trade static pressure for velocity to keep the total energy of the system conserved. Up to this point, we have relied on a frictionless, ideal model. To predict the physical world, we have to account for internal friction. We call this internal friction viscosity. It is the resistance generated when horizontal layers of a fluid slide past one another. The top layers might move quickly, while the bottom layers drag against the container walls. In the 19th century, George Stokes quantified how this friction grips solid objects moving through a fluid. When a small sphere falls through a viscous fluid, it is caught in a tug of war. Gravity pulls it down, while buoyancy and viscous drag push back up. As the sphere falls faster, that upward drag force grows. Eventually, the upward drag and buoyancy perfectly cancel out the downward pull of gravity. The sphere stops accelerating and locks into a constant speed called terminal velocity. Friction governs the interior, but we must also account for the outer boundary of the fluid, the surface. Molecules deep inside a volume of water are pulled equally in all directions, but molecules on the surface have no upward neighbors, resulting in a net inward attractive force that acts like a stretched elastic sheet. This is surface tension. It requires energy to stretch that surface, and this tension is strong enough to drive capillary action, pulling water upward through narrow tubes against the force of gravity. Viscous drag and surface tension act as physical governors, ensuring that fluids obey the practical limits of friction and energy in our universe. We began with the pressure fields of stationary fluids, followed the conservation of energy through moving streams, and finally introduced the friction of the real world. These equations, developed by Pascal, Bernoulli, and Stokes, are not separate phenomena. They form a single continuous mathematical language. Engineers rely on this framework to design hydraulic presses, shape aircraft wings, and predict the flow of blood through the human vascular system. By uncovering this mathematical scaffolding, physics proves that even the most chaotic, shapeless substances on Earth are bound by strict, predictable laws of nature.